Alright, welcome back to the logic slides. Let's finish them. So, we were talking about inference rules, ways to prove things. You have some hypotheses, you have some conclusions. You can use those rules to come up with new conclusions, eventually, until you get at what you're trying to really prove. Alright, so let us kind of go full circle, because normally we're not just going to have P's and Q's. We're going to have like English words, and so we need to get practice going from English words to real proofs. Okay, so here is your assignment. This is a question for you to try after I explain it. So starting from this argument down here expressed in English, I would like you to translate it to pure logic by replacing each proposition with a variable. So find the propositions in this argument, like call them P and Q and whatever else you need, and then prove them. All right. The end result is called, once you translate these things, this entire proof idea, this argument, to variables, that's called you're creating the form of the argument. Okay? So create the form of the argument first and then prove it using inference rules. These ones up here. And you might also need rules of logic as well. Okay, so try that. Try coming up with the form of this argument. So here is the argument. I will buy a new car and a new house only if I get a job. I am not going to get a job. I will buy a new house. Therefore, assuming all those things, I will not buy a new car. Okay? So if you think about it long enough, let's say that P could be like, I will buy a new car. That's something that could be true or false, right? That's a proposition inside of this argument. So I will buy a new car. That's P. Q could be, well, there's a house involved. So I will buy a house. I will buy a new house. That's seen a few times, so that needs to be part of here. So let's call that Q. I will buy a house. B-U-Y, a house. And then I think we need one more. Something about a job, right? So I'm not going to get a job. That could have been our R, or we could just make it the positive version of that. We can negate it later. So I will get a job can be our R. Let's try that. Usually you want to make this the positive version of everything. You can negate them later. And so with that in mind, we can translate this to just pure logic. We can find the form of this argument now. And then we can worry about the P, Qs, and Rs instead of like English words. Okay, so here's the form of the argument. Alright, I will buy a new car and a new house only if I get a job. If you remember, the only if is the arrow in this direction. It's if then. Which is weird to think about. You got your if and only if, remember that. So, take my word for it. I will buy a new car and a new house only if I get a job. So, this becomes, let me just take us back there, because it's confusing. Only if means if then. Where is that? Biconditional. Only if. Alright. It's the first thing, arrow the second thing. That was the if then. Okay? So if then is, only if is really just an implication. There. It's so weird that we have that, but that's it. So I will not buy a new car and a new house implies I get a job. Alright? So I will buy a new car and a new house. That's P, and Q implies I get a job. So that's R. Alright? I'm not going to get a job. So that's not R. I will buy a new house. That's just Q. So those are the things we're really assuming. It's the variables. Therefore, I will not buy a new car. That is the negation of P. That is the conclusion. See that? So yeah, only if is going that way, which is weird. So that's the form of the argument. And now we can use that, we can push around symbols to try and prove this. Okay? So let's try and do that. P and Q implies R, not R, just Q, and then therefore we're trying to prove not P. Okay? So if we stare at this long enough, how can we go from here? places to other places. Let's see here. There's a bunch of different rules that you can use with implications. There's a bunch of different ways to prove things. Like there was a different way that we could have proven this one, for example. We could have used a different rule. But if you stare at this long enough, it looks like something that we're going to need is like the negation, right? We're going to need the negation of P somehow. We can get a negation with, eventually, we can run this one backwards, this implication backwards with modus tollens again. Because we have something implies something, and then the negation of the conclusion. We have all this, the negation of R. That'll give us not P and Q. And that, I mean, part of that involves P. That'll get with like the De Morgan's law, not P in there. Let's see if we can use that. That's one way of trying this. All right, so let's run this backwards with modus tollens. So let's do all that, write it all out. So we need to use modus tollens, the implication, P implies Q, arrow R. We have that, call it 1 by assumption. Whee. And then we need the negation of the conclusion, which we have also by assumption. Okay, that's 2. Let's see, what else do we need? Well, yeah, let's apply the rule now. So now I can get not P and Q, right? That's the negation of the hypothesis with modus tollens on 1 and 2. Okay, so now I have this. That's almost not P. We can bring that negation inside with a De Morgan's rule, can't we? So like this is 3. So this is not P or not Q, right? This is De Morgan's. And sorry, let's call this. I guess I don't have to number all of these because like I'm not using this one. That's just logically implied, right? So we have De Morgan's from, I guess we do need to number them. De Morgan on 3. It's better that way. So now I have this. I need to get the not P out of it somehow. I also have Q. I know that Q is true. I know that this is true. There's actually a way. Let me show you. It's called disjunctive syllogism. So if I have P or Q, and I know that, like, I'm assuming, right, P or Q is true. It's like one of them, if not both, are true. And then I'm assuming that not P is true. That means, well, if this whole thing was true and I know that P was false, that means that Q must have been the one that was true. So I can conclude Q. That's what I need here. All right, I can do that. Let me show that to you. So that is the idea. That's what we're going to need eventually. And it's going to look a little weird, but I promise that's what we want. So in order to do that, right, in order to use this rule, I need the thing that's negated on the left side. Like the negated thing needs to be on the left. That's not P, right? Right now, the negated thing, right, I have Q. Q is not Q, right? I have that, but it's on the right. I need to move it over, okay? That's what we're going to need here. So this is going to be not Q or not P. That is commutative law for or on 4 gives us 5. So now I have it on the left, and then I also, in order to use that, in order to use this rule, disjunctive syllogism, I need the negation of this left-hand side as well, and I have it. Do I have the negation of not Q? Yeah, because I just have Q. I can get the double negation with Q, just by assumption. I can get not Q, because there's a rule for that. There's a double negation law on 6. If I have something, I also have its double negation. That's also true, right? That's the double negation rule. And now I have this and this. And this is the negated left side of Q. I can finally use this disjunctive syllogism rule to get out the other side, which gives me the right-hand side. Okay, so I'm going to be able to get, finally, not P, this is my last conclusion, by using the disjunctive syllogism rule, disjunctive syllogism rule on, let's see, we have 5 and 7. Let me prove that to you. So in the disjunctive syllogism rule, my P is the left side of the OR. My P is not Q. P is the not Q, and my Q in the rule is the right-hand side. It is the not P, okay? And I had the negation of the P in the rule, which was my not Q. I have not Q, here it is. And so I can run the rule and get out the right-hand side, which is the rule's Q. It's weird to think about, I know. You have to like shuffle around all these variables in your brain. It's just the right-hand side. I can get that out. And that was the not P, okay? And that is my conclusion. That is why it's a valid proof, okay? So we went from English to the form of the argument. I guess we want to separate that kind of. And then we went from the form to the proof. It is a valid thing to prove. Okay? So please yell at me if you have any questions about that. But this is the kind of level I want to get you at. All right? There are also rules of inference like these, but with quantifiers involved. That makes it easy to start proving quantified things. So let's talk about that. If you'd like to prove a quantified statement, you have to eventually remove the quantifiers, which is weird, because then you're not talking about everything at once, but you kind of are. So I'll show you why that works. You have to be very careful, though. If you move the quantifiers in the wrong way, if you remove them improperly, the argument goes wrong, and it's not true what you're saying. So you got to be very careful. The way that it works is you replace quantified variables with either an arbitrary element of the domain or a particular element of the domain, because remember, there's always a variable involved. And I'll show you what that means. An arbitrary element cannot be special. It's supposed to stand in for every possible element of the domain, and that's how we can get out of a for all quantified statement. We can get rid of the quantifier if we make an arbitrary element of the domain. And then we can make a particular element of the domain whatever we want. It can be a special element. Like you can pick 42 for your particular element if you'd like, if that lets your proof go through. Or you can just assume it's there. You got somebody in the domain such that it works. Okay? So there's also a big difference between proving a quantified statement, like proving that a for all is true. That's part of your conclusion, right? Or using versus using the quantified statement as just a hypothesis. What can you get out of it versus what do you need to show to prove it, all right? So it's going to come down to these arbitrary elements versus particular elements, and this is going to be the key of proving or using quantified statements, all right? Let's talk about proving versus using some more, because it really is a little subtle. When you're proving something, you have to show that the conclusion is true, right? But you get to assume that your hypotheses are true. That's using, right? You can use your hypotheses to prove something bigger. Right? So to prove, for example, a for all quantified statement, you have to prove that P of A is true for an arbitrary element A. Right? That's how this is going to end up working. So to prove for all x P of x is true, you have to prove that, just show that P of A is true and assume that A is anybody. Okay? If you don't assume anything special about A, like it gets to range over every possible value, then every element of the domain must have worked. See how that proves a for all? More examples will make this make more sense. If you want to prove there exists, you have to show that, all right, some value in the domain, some arbitrary or particular element B works, and it goes through. You just got to find one good element, or just show that it exists without picking what it exactly must be. Okay? So that's how you prove it there exists. Just find one good element, call it B. And then you can get rid of that there exists and just work on the P part. All right? it's different to prove versus use. If you have this in your hypothesis, you know, like you get to know, you get to pick out P for any possible X value in the domain. You know that it's true for all of them, right? If you want to use this as a hypothesis, you can produce P of A for any element in the domain, right? Because you're assuming P of X is true for all X, so take any element of the domain that you need, and you know that P is true for it, because you know that it's true for all of them. You see that? Likewise, to use that there exists, you just know like there's some element in the domain such that P of X is true. Well, call it B. Let's start using B now, right? There's one particular element for X in that domain such that P of X is true. That's what this means to assume that. We're just not sure which one it is because this doesn't have that kind of information in it. So we'll just give it a name, call it B, and we know that P of B is true. So there's at least one element such that P of X is true for some X, all right? So here are your rules of inference, just in the normal inference form. Here's how you can use them to either prove or use these values, okay? Back to using though, there's something that I forgot to write down. If you're using for all X P of X, like you can just pick out any element, like, all right, I know that P of A is true because A is in my domain. I know that P of B is true because B is in my domain. Same for C, ... For any element you need, you know that it's true. That's what I'm trying to say there, right? So here is this in fancy diagram form. So here are our rules of inference. You got universal instantiation. This is saying, all right, if you have for all X P of X as a hypothesis, and you know that C is some element of your domain, then you know you can prove that P of C is true, right? This is using for all as a hypothesis. You can pick out some element of your domain. You know that P is true for all of them, so it's true for that particular one that you care about. All right. This is how you prove a for all when it's your conclusion. All right. I guess I should say proving for all. Here it is as the conclusion. If you assume that C is an arbitrary element of your domain, and you can still show that P of C is true for that random element, it's arbitrary, it could be anybody, then you've shown that it works for every possible element of your domain. You know that for all of X, for all X, P of X is true. Does that make sense? It's a little weird to think about. Examples will help it make sense, but that's the idea, all right? That's universal generalization. And then here are the other two. This is using, existential instantiation is using there exists as a hypothesis, and then existential generalization is proving there exists as your conclusion, right? So here is existential instantiation. If you get to assume that there exists an X such that P of X is true, then you know that there's some element of your domain, call it C, and P of C is true for it. Because you know that at least one person has P true for it. At least one X. Call that XC. All right, that's how you can instantiate a variable. All right. Though, you got to be kind of careful when you're using this rule. Each use of existential instantiation must define a new element. Like, you can't say, like, all right, this gives me a C, and then I have some other there exists, like, with, like, a Q, and I can also make a C from that. Like, it's the same C now. No, that's wrong. Because that, like, links things that shouldn't be linked. So every time you use this rule, you must define a new element with a fresh domain, with a fresh name. Like, if you already use C, the new variable that you make has got to be called D now. Okay, it's got to be a new variable name when you're instantiating an existential hypothesis. All right, that's using there exists. You can prove there exists pretty easily. It's like, all right, if I have some element of my domain and I've proven that P is true for that element, then I have found one good element such that P is true. So there exists an X such that P of X is true, well, because I found the C. X can be C. It all works out. That's how you can prove there exists, right? And so I think the next thing to do is give you an example before I have you try all this. All right, so here's an example for us to try. All right, so here's my argument. I have these two assumptions for all X Q of X is true or P of X is true. I know also I'm assuming that for all X not Q of X is true, and then I'm trying to use those to prove that for all X P of X is true. So no matter which X you pick, P of X is true for it. So I'm trying to in my conclusion, prove a for all quantified statement. The only way to prove a for all quantified statement is to use this rule, universal generalization. So I need, what do I need? I need some arbitrary element, I can pick it, and then I need to prove just P of C for that arbitrary element. As long as I don't make any special assumptions about C, it works for everybody. Therefore, I have proven a for all thing. All right, so the only way I'm going to get this is if I have some P of C and I prove that it's arbitrary, and I prove that P of C is true, no matter what. So that's really my goal, because the second I have that, the second I have P of C for some arbitrary element C, I have gotten my for all x P of x. Does that make sense? That's the only way I can get it anyway. And so the only way I can get it is using these things now. Those are my ammunition. That's how I'm going to be able to obtain my conclusion. I must use my hypotheses. That's the only way I'm going to get at stuff. So I can get a P by using this rule, right? That'll give me something or a P, probably with the help of this rule as well. Okay. So how do I use those for all quantified things in my assumptions? I use these. I use this rule of inference. I know that I have this for all quantified thing over some predicate. I can pick out a random element, an arbitrary element or a particular element. I'm going to need an arbitrary one. You see that? And then I can, knowing that P of x is true for anybody, I can prove that, I can show that P of C is true. I can get that out of that assumption. Okay? So that's going to be how I start. I'm going to try and make this a little bit more like English, less like a table like last time. That's where we're going with all this. But the first thing I'm going to do is, well, I need to apply these universally quantified rules over some element of my domain. So I need to obtain that element. Let's say that I have an element. All right. So here's how you do that in math. You say let C. It's like a variable declaration in math and a proof. Let C be an arbitrary element of P's domain. All right, now I have it. I need that because I'm going to eventually be using universal generalization to get my for all x P of x. I'm going to need that later. All right, so that's part of universal generalization and also instantiation, like I need it up there too. But that's just part of the game, all right? So this is part of for all generalization, blah, blah, blah. Okay? So once I have that, I can use this rule to obtain, now that I know I have a C, I can use this rule in my C to obtain P of C for that thing. And what is my P but this giant thing? So I can obtain, based on this, I can plug in X and get out Q of C or P of C. All right, so now I get Q of C or P of C. I know that that's true based on this rule and the fact that I have a C. Okay, and that is part of for all instantiation. That's using a for all in my hypothesis. For all instantiation. Lots of writing for me. All right, I can do that. And then also, I can use this rule. I can instantiate that X. It works for anybody. I can get out not Q of C, right? Because I have some element of my domain. This is a for all thing. That's got to be true for everybody. That not Q of whatever is true. I have a C. It's true for that C. All right, and that's, again, for all instantiation with that other hypothesis. So for all instantiation, again. Okay, so now I have these two things, and notice they have no quantifiers anymore. I was able to get rid of those quantifiers by going to just arbitrary elements of my domain, which is beautiful because now I can use normal logical rules. Okay. For example, I have an OR and I have a negation of the left side of that OR. What can I do with that but disjunctive syllogism? I have an OR, I have the negation of that left side of that OR, which means the other side must have been the side that was true. So I'll use that, disjunctive syllogism, to get, now I know that I have P of C. That's what disjunctive syllogism gives me. And now I can conclude, right? I have an arbitrary element in my domain, and I've proven P of that arbitrary element. What do you know? I now have proven a for all. C could have been anything, and so it works for everybody all at once. Therefore, I have for all x P of x, which is what I was trying to show, and that is from universal generalization. Universal generalization with, let's give numbers to these things that I'm using down here. So with, well, I needed the arbitrary C, and I needed to prove P of C, so with 1 and 2. All right, so that is my proof. I've gotten rid of these for alls in the hypotheses by taking out some arbitrary element of my domain. That gives me these for those arbitrary elements, for that one arbitrary element. Then I have P of C, gotten with just normal logical inference rules, and then I can get my for all using the rule for obtaining a for all. Isn't that neat? So that's a more English-like proof. That's kind of where we're going in this class. So I want you to try that for this example. So prove that this argument down here is valid. Read it. The first thing you need to do is translate it into like math. Find the form of the argument. Make variables for the predicates or the propositions, whatever appears. It'll be only predicates for this one. And then express everything using those predicates, like make up a P, make up a Q, stuff like that. All right. Then use the rules of inference, all these ones, and then just the normal rules of logic too, to prove that that form is valid, which proves your argument. Okay. So give that a try, and then when you come back, I'll do it. So first of all, we need to find the form of this argument. So the domain is the set of athletes on a team. Cool. That's kind of not part of the real argument. It's just telling us about the domain of these predicates that we have to come up with. Everyone, which means every athlete on the team, everyone practices hard or plays badly. Okay, those sound like, or both. Those sound like predicates to me. Someone does not practice hard, so that's part of the practices hard predicate, and then plays badly shows up again. So I see two predicates. P of x, define that to be x practices hard. It's a predicate, right? It depends on who you're talking about. Practices hard. And then we have Q of, doesn't have to be x, call it y, saying that y plays badly. You could also define this as y plays well and just negate it to mean plays badly, but I'll just do it like this. So with that in mind, we have the form of our argument. Pretty easily obtainable now. So everyone practices hard or plays badly. So for all, right? Everybody, quantify over every athlete on the team. Either they practice hard, that x practices hard, or they play badly. And it's x now, because that's the name of the variable that's quantifying over all the players. All right. Someone does not practice hard, so there exists, right? There exists an x. Again, I could say exists a z if I really wanted to. There exists an x such that that person does not practice hard, so not p of x is true. And then the conclusion is, therefore, someone plays badly. So there exists an x such that q of x is true for that person, because that means they play badly. Okay, so that is the form of the argument, and with that, we can go and prove it using the rules of inference. So we have that, oops, wrong color. We have that for all x, for every athlete, p of x is true for that athlete, or q of x is true. We have that there exists an x such that not p of x is true, so somebody does not practice hard. And then we're trying to show, therefore, that there's somebody who plays badly. So there exists an x such that q of x is true for that x, for that athlete. And so we're trying to end up with a there exists. What do we need to do in order to get that? So in order to get a there exists, I need some arbitrary element in my domain, and I need to prove that P, my predicate, whatever it is true for that particular element. My predicate's called Q for this proof. Okay, so just replace P with Q in this, and that's kind of what we're doing. We need some element. We need to show that P of my predicate's true for that random element in my domain, either arbitrary or particular, and then I found my one thing. I found somebody for which this predicate's true, therefore there exists somebody where the predicate's true for them. It's pretty logical, right? So I'm going to need somebody, and the way I can get at somebody is I can arbitrarily pick somebody and know that P of pick somebody, call them C, and I know that P of C is true for them and Q of C is true for them. Or I can use this one. I can take apart this existential quantified thing, because if you know that something is true for somebody, that means there is some particular element and the predicate's true for them. So let's do that one. That's how we'll take apart this idea. Okay, so let's pick this one apart with existential instantiation. All right, so let C be an athlete. That's part of what the predicate entails, right? Athlete. And that's the first part of existential instantiation. That gives me somebody. And then I also get that the predicate's true for that somebody. So what's true about this somebody, about this thing, that there exists an X such that not P of X is true for them? Well, I know that not P of C is true for that particular athlete called C. All right? So that's what existential instantiation gives me. It gives me some athlete such that the predicate, whatever it is, after the quantifier is true for them. Okay? And now, I also have a C. I can use that C here. I can pick apart this for all quantified thing, because all I need was some element, and that in my hypothesis, then I know that the predicate's true for that random element, because it's supposed to be true for everyone, right? If I know this is true for anybody, I can plug in C. So let's do that. I also know that P of C is true, or Q of C is true, and that's for all instantiation. It's picking apart the for all. Okay, and then, okay, it's disjunctive syllogism all the way down again. So I have an or, I have the negation of the left side, which means that I can get the right side. That must have been the side that was true. So that gives me Q of C better have been true. And that's done by disjunctive syllogism. You can write out numbers if you'd like as well. Syllogism. Okay. And now, what do you know? I have some arbitrary element of my domain. I've proven that Q of C is true for that particular arbitrary element, which means there's somebody, particularly C, for which there exists an X. Q of X is true. All right, so that gives me what I want. There exists an X such that Q of X is true, because I just found one, right? Here it is. Found that element, and I found the predicate for that element. So yeah, there of course is somebody for which this predicate's true. Here they are. Does that make sense? So therefore, I guess is what I should be saying. And that was existential generalization. With, we can start using numbers here, with we needed the element, and we needed to show that the predicate's true for that element, with 1 and 2, let's say. Okay, so that is a good start at these proofs. Maybe it's still very, very confusing to you and difficult to get at this, but all I wanted was you to try here. You'll be trying some more in your homework, and I hope it makes a little bit more sense there. Okay, so that is the end of these slides. I will go and use the magic of video editing to open up the next ones, and we'll get a little bit of a head start on the next slides about proofs. Okay? All right, welcome to the proofs slide. So this is the place where we're going to hit hard the idea of writing a proof. We talked about it a little bit in the logic slides. We needed to go through all those like tables and plugging and chugging things just to be able to get to this point. Modern proofs, like normal mathematical proofs, are written like English, but everybody has those tables that we were doing in the backs of their minds, and that's how you know that it's correct. So we needed to go there first in order to get here and make it all pretty. But let's, without any further ado, start talking about proofs. Okay, so yeah, let's start learning how to make it happen, learning how to write more English-sounding things. But first, I kind of want to motivate like why you might want to do this. This is a very important piece of your mathematical journey, and so I want to like get philosophical for just a slide, and then we'll go back to the normal mathy stuff. So proofs, learning how to do proofs is a very important part of becoming a mathematician, and as a computer scientist you kind of have to be one. You have to be a mathematician just a little bit for the rest of your computer science career, and learning proofs is the start of what's called higher math, higher mathematics, and that can sound a bit snooty, and it kind of is justifiably so, because it is much cooler than the math maybe you've seen so far in your just educational career. So I'm here to tell you that if you hated math up until now, and the reason why was because you were like plugging in numbers, computing values, even calculus to some sense is kind of boring in the sense that you are just computing numbers. You're finding an integral, you're finding a derivative, all these things that don't make a lot of concrete sense unless maybe you've taken a physics class. Maybe calculating things is what you thought math was, and I'm here to tell you that's not true. So if you hated math up until now, you might enjoy where we're going here in this class. Things that math majors learn, this so-called modern math, I consider to be very beautiful. Okay, and it also has nothing to do with numbers in a lot of the branches. It's very abstract. It can be very abstract. There are, of course, fields like number theory where you do go back to numbers, but there's a lot of other fields of modern math that have nothing to do with that. Okay, when you take upper division computer science classes, you're going to notice that you need all the stuff that we're talking about here. So that's why we're hitting it hard. We're learning all these definitions. We're practicing them a lot. That's why we have to have a little mini math class in computer science, okay? Another cool thing is you can relate this back to programming. If you like programming, and you probably do if you're here, proofs, writing a proof is essentially like writing a program. There's a very strong correspondence that is true about those two things, all right? And also, just writing proofs, it's like almost writing an essay, writing or drawing a picture. It's kind of like an art form, just like writing a program is, okay? So you're going to see some very cool proofs, and I'm excited to teach you them. I think that they're very beautiful, okay? And I say this because maybe if I could go back and try all over again, maybe I double major or just major only in math, because I think it's that cool after I learned about this kind of cool stuff. So yeah, that's my rant. Let me continue now with your regularly scheduled computer science. So in order to start with all these proofs, we have to learn definitions first, just as usual. So let's talk about those definitions. And we're going to convert them to logic as we go, because that's a good practice. We always have to be thinking about the formal definition of things. Like English is not good enough for us anymore, okay? So, all right, this is a term you've heard before, right? An integer is even if there is an integer k such that x is equal to 2k. This is how we define evenness. Okay, does that make sense? We have to formally specify what we're talking about, because English doesn't cut it anymore. So an integer x is even if there is an integer k such that x is equal to 2k. So it means we know that a number is even, call it x, if there exists a k such that x is equal to 2 times k. It's an exact multiple of 2. That's what it means to be even. Okay? You think about it long enough, that makes sense. Odd is the opposite, kind of. An integer x is odd if there's an integer k such that x is equal to 2 times that k plus 1. There's 1 left over, right? There is a remainder going on there. So this is an odd number. Every odd number looks like this. You can find some k such that your odd number is equal to 2 times k plus 1 left over. Okay, it never goes in cleanly. All right? So maybe you never thought about these things. Now we have to think about them if we want to prove that numbers are even. Formally, prove that numbers are odd. Okay? So let's keep going. So a number r is rational. First of all, integers are just whole numbers, like 0, -1, 1, all that stuff. A number is rational, we say, if it looks like a fraction. A number r is rational if there are integers x and y such that y is not equal to 0, because you're going to divide by it. You can't divide by 0. And r is equal to the ratio of those two numbers. That's why it's called a rational number, x over y. All right? So in math form, A number r is rational if there exists an x and there exists a y, such that y is not 0 and r is equal to x over y. So that's what it means to be a rational number, or just a fraction, okay? That's the idea. It's a fancy term for that. We say that a number x divides another number y, the integers again. Integer x divides an integer y if and only if x is not equal to 0 and y is equal to k times x. We say that 0 doesn't divide anything, or maybe it divides everything, who knows. But the number is not 0, it divides y if it times some integer k is equal to that y. Does that seem normal to you? So we say that a number divides another number if we've been able to find some k such that we can multiply that number that we say divides it, and we get that original number. Okay, so let's define this with a symbol. We'll use this symbol to mean x divides y. You can read that little pipe character as divides y. So x divides y if and only if, biconditional, there exists a k such that y is equal to k times x. And this is a bit of a weirder definition, so let me give you some examples. For example, 2 divides 4. 3 divides 9. Does that make sense? Because you could multiply 2 by 2 and get 4. Because you could multiply 3 by 3 and get 9. Maybe I should say 3 divides 12. Because then you could multiply 3 by 4 and get 12. It's always implicitly saying you can find some k and multiply that first thing by k and get the number you're talking about. It divides it. All right? It goes into it cleanly. You can flip this around and say, if you know that x divides y, then you can talk about y. Y is called the multiple. Y is a multiple of x, right? 4 is a multiple of 2. 12 is a multiple of 3, right? And then x could be also called a factor of y or a divisor of y. So those are a bunch of different similar terms that I'm sure you've heard before, but maybe never made precise. Now we're making them all precise so that we can use them in our proofs. All right. A integer n is prime if and only if that number is greater than 1, and for every positive integer n, every positive integer m, if m divides n, then m is equal to 1 or m is equal to n. That's a very flowery mathematical way of saying precisely that a prime number only has factors that are 1 in itself. Does that make sense? So we have to translate it to this kind of mathy stuff so that we can prove it, right? We need it to be very precise. So let's define n being prime to mean if n is prime if and only if. And let me show you how you can translate all this fancy, long-sounding English to math. So n is prime if and only if it's greater than 1, and for every positive integer m, all right? For every m such that m is greater than 0, and it's an integer, you can say that too if you want. Let's just implicitly consider it to be an integer. If m divides n, so first of all, it's positive if this is true, right? So for every positive integer m, so for all m such that if m is greater than 0, then if it also divides n, if m divides n, there's two implications going on here. If that's true, then m is equal to 1 or m is equal to n. Then m is equal to 1 or m is equal to n. 1, 2 close. Does that make sense? So that's how you could translate that to math, and then you'd have to prove this. That's pretty cool. An integer n is composite if and only if it's not prime, kind of. You could use the negation if you'd like. Or you could define it like this: if and only if n is greater than 1, and there's an integer m such that that m is between 1 and n, and it happens to divide n. So you can find a factor. An integer is composite if there's something other than 1 in itself that goes in cleanly. That is not a prime number. That's a composite number, right? So write that down as well. N is composite if and only if n is greater than 1, and for there is an integer m. So there exists an integer m such that m is between 1 and n, and not either of them, strictly less than, strictly greater than, and m divides n, okay? So this is very similar to the opposite of this, okay? You're still considering only numbers greater than 1 there. That's the idea. So that's a composite number. That's how you can define that. All right, so the reason we did this again is so that we can prove these things beyond a shadow of a doubt. Like, I know a number is even because I have found this k, right? Something like that. So let us use the rules that we learned from our previous slides and write a more English-sounding proof, okay? This one is just using the definition, though. So here, I'd like you to use this definition of evenness on this slide. Here it is. Or use the English. I'd like you to show that the integer n is, well, figure out whether or not it's even or odd, okay? I think I've given you the answer, right? If it's even, show that it equals 2k for some k. If it's odd, show that it equals 2k plus 1 for some k, all right? Because that's the definition of those things. So do that. Write it down, all right? That's my problem for you. And so you will write down this, right? This is what you should have said. N equals 42 is even because n is equal to 2 times 21, right? And that 21 is my k. Just choose k to be 21. Oh man, I have found a number such that it times 2 is equal to my number that I originally had. All right? And that means n is even. That's how you define it. That's how you prove it. I hope that makes a little bit of sense. Okay. Another interesting thing is pushing in a negation on an inequality. So I want you to push that in and figure out how that works. All right, so write the following without the negation. How does this change? What does it mean for x to not be greater than 42? What does it mean for y to not be less than or equal to 100? Okay, so give that a try. See if you can figure it out. When in doubt, I'd like you to go to the number line. It's been a while since we've gone there, right? So I'm saying that it's not true that x is greater than 42. So first of all, what does it mean for x to be strictly greater than 42? Well, you go on the number line, here's 42. It's strictly greater than, so not including that, and then everything onwards. That is what it means for it to be greater than 42. I'm saying it's not true that it's greater than 42. So that means it's either exactly 42, right, because that wasn't considered. It's everything that's not highlighted. It's everything over here, right? So it's either 42 or less than that. So the flip side of this is x less than or equal to 42. Did you get that? And so that's going to be the pattern. You're going to flip it and maybe add an equal sign or take away an equal sign. So what does it mean for y to be less than or equal to negative 100? Because we're going to flip that. Less than or equal to negative 100. So here's negative 100. For y to be less than or equal to negative 100, it could be negative 100 exactly, or it could be anything less. And I'm saying that's not true. I'm negating it. So what's true then? If it's not any of these highlighted things, that means it's either it's not 100, can't be 100, it's strictly greater, and it's something over here. So it's only greater. Y is strictly greater than 100. That's the opposite of less than or equal to. Sorry, does that make sense? So that should be negative 100, sorry. I hope that makes enough sense. So you just flip it all. And so that's the pattern. Just use your number lines if you need to. You negate a less than, that becomes greater than or equal to. Negate a greater than becomes less than or equal to. Negate less than or equal to, that becomes strictly greater. Negating greater than or equal to becomes strictly less. And negating equal to and not equal to, well, equal becomes not equal becomes equal. And let me prove that to you. So like the negation of x being equal to 42, well, that's equivalent to saying that x is not equal to 42. Does that make sense? It's not true that x is 42. That one's easy. I don't need to use a number line for that one. The negation of x not equal to 42, though, that's kind of like a double negation. So let's draw that. So if x is not equal to 42, here's 42. If it's not equal to 42, that means it's just something other than it. So it's not including it, but it could be something over here, could be something over here. So you negate it by taking only the things that are not filled in. The only thing that's not filled in is it being exactly 42. So that's going to be the opposite. Okay, So that's how you negate comparisons. That's going to come up forever. So now you know. All right. We're not going to actually prove any real things. These are technically proofs, but we're not going to get any fancier than that until next time. So let me just give you a little sneak peek, and then we will end this lecture. So our goal is to be able to prove things called theorems. All right, a theorem is just some statement that you can prove to be true or false, something that you can argue, right? So to prove a theorem, you can do anything that is logical. So you can use, of course, just the basic rules of logic that we learned in the previous slides. You are allowed to use any assumptions that you made, either in the proof statement or somewhere else, because that's totally part of it, right? You're allowed to use your hypotheses. That's something you can use to prove your theorem. There's also some things that can just be lying around that you can just grab and use. Those are called axioms. Those are statements that are assumed to be true outside the proof statement. Like, I don't know, I can't think of a good axiom of arithmetic off the top of my head, but like you could start defining integers by just saying like the number 0 exists. That's just something you take for granted. That could be called an axiom, okay? Your book probably talks about that a little bit more, so go there if you have any questions about it. But you could also, in proving a theorem, you can use any previously proven statements in theorems. So a nice goal of mathematics is to just start from the smallest amount of axioms and then build up everything that we know about numbers, for example. All right? So let's build up all of math little by little, just a theorem at a time. You can use old things to prove new things. It's like calling your old functions that you wrote, right? That's how you can prove theorems, by using old things. Build them all up. So that means a proof has the following form. And it's exactly what we were talking about before. It's just like an argument. You have a bunch of assumptions, assume that those are true, and you have a bunch of previously proven theorems. You know that those are true. You can get at them, but you don't have to prove them all over again, so you can just assume that those are true as well. If all of that is true, you're assuming that all those things are true, and you're using them to prove your conclusion. So if all these things are true, then the conclusion must follow. All right? And then you use logic. You use all the rules that you know to go from these hypotheses and these previously proven theorems. Those are your firepower. Those allow you to get at your conclusion. All right? And logic builds the path for you. And so that's why we had to learn it first. But now we're ready to talk a little bit more about proofs in terms of English. So like this is a bit more English-like because we took that detour to pure logic, and we know how to write this stuff now. We know what it means in the back of our mind. We don't have to keep writing it down, right? We can use more English-like stuff. And that is a great starting point. And that's going to be the end of the lecture for today. So the next place I will see you is in your lab video.